Now, let's go through the CoALA architecture. I've included the reference to CoALA here. I'll also briefly mention how Voyager and generative agents fit into CoALA, and in a later part, I will do a deep dive on how each element in these works map onto the architecture. This is the diagram of CoALA from the paper. Note that most of these elements here have equivalents in recent works. In CoALA, memory structures are divided into two broad categories, long and short-term. The only type of short-term memory here is the working memory. It contains readily available information available to the agent. The working memory acts as a central hub in the architecture. Note how it connects to all other components via the arrows over here. In generative agents, this is mostly represented by the scratch memory. Moving on, we proceed to the long-term memories, namely the procedural memory, semantic memory, and episodic memory. The episodic memory represents the past experience of the agent. It is closest to the plain English meaning of the word memories, for example, the sights and sounds of a place you visited yesterday. In reinforcement learning, this is commonly used and is known as the replay buffer. It can also contain things like the training data. In generative agents, this is represented by the raw observations and events in the memory stream. The semantic memory represents the agent's knowledge of the world and itself. In retrieval-augmented generation, this is represented by a database, and it's no coincidence that the authors use a database icon here. In generative agents, reflections are stored in the semantic memory. The last type of memory, the procedural memory, represents the skills of the agent and can be classified into two types, implicit and explicit. Neural network weights are implicit as they perform skills, but are represented by not so interpretable numbers. On the other hand, the agent code is explicit as it is human readable, and this implements actions and the decision procedure, which we will discuss later. In Voyager, the skills library is an example of the agent code. In CoALA, actions are classified into external and internal types. This is not necessarily the action in the plain English sense of the word. The only external action, the grounding action, is the closest to the action we know in plain English. It represents the agent's interactions with the environment, be it in dialogue for chatbots, the physical world for robots, or the digital world for web and game agents. Internal actions describe the interactions between the different types of memories and the decision procedures represented by all these arrows within this box, which represents the agent, hence the name internal. The reasoning action reads from and outputs to the working memory, generating new information. The key difference between cognitive architectures of the past compared to the present era is that previously, reasoning was limited to hard symbolic logic, which might require handcrafted rules, while today, reasoning is an action that emerged in large language models, so we can ask a model directly to perform approximate reasoning. In Voyager, this is represented by the curriculum agent deciding on the next task, or the action agent writing code. In generative agents, this is represented by daily planning. Retrieval actions extract information from the long-term memories, as you can see the upward pointing arrows here. In Voyager, the skills manager retrieves code that might be relevant in completing the task from the procedural memory via dense embeddings. In generative agents, the reflections, chats, and events are extracted from the semantic and episodic memories during the reasoning process, using a score that factors the relevance, importance, and recency of the memories. The learning action writes new information from the working memory to any of the long-term memories. The first type of learning updates experiences in the episodic memory. For example, in reinforcement learning, we store transitions to the replay buffer. In generative agents, chats and observations are stored into the memory stream. The next type of learning action updates the knowledge into the semantic memory. In both generative agents and reflection, which citation is here, the reflections are stored this way. The last type of learning action updates the procedural memory. For the implicit type, this is the fine-tuning of model weights which we are familiar with. When updating agent code, recall that we have 4 types of actions that we can update: the grounding, reasoning, retrieval, and learning, and also the decision procedure. In Voyager, the skills library is updated by adding code that was used in successfully completed tasks. In 8, which I've included the reference here, the prompt templates are being updated. For retrieval, learning, and decision making, the authors were not aware of recent works that cover this. So to the researchers out there watching this video, this is an opportunity to make a contribution. A major point to note is the additive nature of most learning methods currently. This can occasionally cause problems. For example, in generative agents, the believability of the agents surprisingly decreases as the knowledge expands. The authors then highlight 2 understudied areas, the first of which is modifying the memories. For example, in GITM, which reference I've included here, the skills actually undergo consolidation, whereby the set of skills that accomplish a task are consolidated every few steps. The other understudied area is deleting memories. For example, in Google's first machine unlearning challenge. The last part of the architecture is the decision-making process, or how an agent chooses an action to take. So this diagram right here is pretty much self-explanatory, so I'll just highlight the non-obvious parts. So during the proposal stage, the agents use the reasoning action and potentially the retrieval action to generate candidates. Then a subset of these are sampled depending on the methods. So for some scenarios, the action space is really small, so it's still possible to sample all actions. There are also other methods that use different techniques like hard logic or planners. In the evaluation portion, there are various ways to perform this. For example, you can use heuristic rules, LLM values, learned values, for example, the value function in deep reinforcement learning. You can even ask the LLM to reason, for example, in generative agents, whether an agent decides to react to an event is decided by an LLM. And another trend currently is to ask the LLM to do internal simulations to see what will happen if the action is taken. Another trend to note is making the proposal and evaluation an iterative process rather than a single stage. For example, using this diagram from Tree of Thoughts, which I've referenced here, most current techniques only propose and evaluate in a single stage, and there are also other techniques that expand reasoning steps in a linear fashion. In Tree of Thoughts, promising candidates are then further expanded using systematic tree search like depth and breadth first search.